Dr. Mejias is assistant professor of chemistry and co-director of the Precision Design Institute at the University of Puerto Rico. She's currently working at Amgen, but the topic of today is from her work at Puerto Rico, and we're looking forward to it. She's been one of our users for many, many years, and thank you for your time for coming over.
So this work, although I'm currently affiliated with Amgen, this work was produced at the University of Puerto Rico Rio Piedras campus, my previous affiliation. So today I thought I would tell you a little story about how you can do, how you can go beyond crystallization using the crystalline. And this story starts with describing titanium dioxide as a material that is very well known across many industries and applications. And it, it is also common to think about titanium as just one form, but in fact it has three polymorphs, rutile, anodized, and brucite, which you can access through different methods. And we're going to discuss that in a little bit. But we thought about using titanium because it has applications such as drug delivery and biomedical applications that can potentiate its effect for bone-related diseases. So that was part of my research at UPR. What we wanted to do was to use this material, titanium, after photoactivation to functionalize that material with crystals that had already shown us that they had an effect in potentiating cell death of metastatic breast cancer. So I guess our design of experiments started with making rutile-phase TiO2 in some way. I'll describe that way in a second. And then making the coordination complexes that are based on biphosphonates. Biphosphonates are drugs that are used for bone-related diseases such as metastatic breast cancer. And I guess we wanted to combine it into a single multifunctional material that can help us treat that disease. So we're gonna make the titanium, we're gonna photoactivate the titanium, we're gonna use surface crystallization to embed crystals of a material that has affinity to the bone and reacts against metastatic breast cancer cells. And we're gonna have that material made in a novel way. So I guess the first part of the story is how do we make that biphosphonate-based coordination complex? So we have zoledronic acid. Zoledronic acid is a third-generation biphosphonate. As I said, biphosphonates are used to induce osteoclastic bone inhibition. So that means that it preserves your bones matter, right, as it reacts on the surface of that material. We're gonna coordinate it to make coordination complexes with calcium, magnesium, and zinc, which are also bioactive and involved in bone regeneration stages as well, these three metals. And so we basically explore different variables to make these materials, the metal to salt molar ratio, the salt anion, the reaction temperature, and the pH. And these crystals, these 6 phases that were produced, salt calcium form 1 and form 2, salt magnesium form 1 and form 2, and salt zinc form 1 and form 2, were made in either the crystalline or the crystal breather. So we use those in a reaction crystallization systems to carry out these crystallization experiments as part of our searching for these crystal phases. So once we had the crystals, obviously being in a crystallography background, I solved the crystal structure of these materials. It was not difficult because the crystals were very good quality. And these are the unique structures versus the structures that were redetermined from the literature. From this material, we decided to go, because of several reasons, with Solca Form 2, ahead with the different other crystallization experiments that I'm going to talk about. So selecting Solca Form 2, now we are going to do or utilize phase inversion temperature method, emulsification method, to develop these crystals not in the bulk material, but in the nano range. And I say nano range because we fell 50 nanometers short of what the definition, the purest definition of nano is. So in the phase inversion method, we start with oil in water immersion, okay? And we change the temperature to end up with a water in oil emulsion. And as you can see from the figure, the size of that droplet, initially an oil droplet, and at the end of the phase inversion temperature, a water droplet, reduces. And that reduces the volume where the crystallization happens. So this occurs in a crystalline. So we use the crystalline to carry out the phase inversion temperature method. We have our salt and our calcium. We added, I would say, dropwise is the word, and we come up with the material nanoca salt, okay? A material that, as you see in the DLS image, is around 150 nanometers in size. We also tested the aggregation behavior of that material in biorelevant media, and the material doesn't aggregate over time in this physiological media. The other thing that we did with this material is we use hydroxyapatite to model the bone environment and to assess whether this material, the coordination complexes, was still a high affinity to the bone. And as you can see, SOL, which is the black trend line, falls short at 24 hours relative to the nanomaterial, mostly because the nanomaterial has higher surface area and is able to bind more faster than that of the ligand alone. And these are some EDS analysis that allows us to confirm that in the surface of hydroxyapatite, we had the binding of this nanomaterial. So once we had this nanomaterial, I guess the next step in our design of experiment was to develop a method that would allow us to get the 3 different forms of titanium using just a single process, okay? Titania is, as I said, very well explored. There's multiple methods, but the methods are not specific to, their methods are specific. So you need one method to generate phase pure, in parentheses, right, or in quotations, titanium. But we wanted a method, right, that would be just a single method, greener, lower pure toxic compounds, lower energy, that would allow us to access all of the 3 forms, and that we did using the crystalline and the phase inversion method. So using the phase inversion method, starting by aqueous emulsion with different compositions. Some of them are highly acidic, some of them are highly basic, some of them are intermediate in pH. We were able to carry out the crystallization using, again, the phase inversion method in the crystalline under specific conditions. And the only thing that changed was the aqueous phase in which the titanium nanoparticles grew and the calcination temperature. Nothing else in the process changed. And we were able to isolate each of the 3 forms of titanium, brookite, anodized, and rutile, using this method. So now that, so I guess I have here a comparison of the size of the particles without using the crystal 16, just using it in a, just an ICA plate or a heat plate, right? And you can see the difference, right, in whether we do the phase inversion temperature outside of the crystalline, where we get very broad particle size distributions, and doing it in the crystalline, where even if sometimes we got bimodal distribution, the sizes were controlled by that phase inversion temperature, by that accurate temperature profile that we did in the crystalline. The other thing that I have here to show you is, I guess, evidence that these are phase pure titania of 3 different phases. Many of the methods that I talked to you initially produce different phases of titania, but you can question whether or not these are phase pure. So this is the Raman and XRD spectra. As you can expect, the XRD has no diffraction because we have, before the thermal analysis, amorphous TiO2. After we calcinate the material, then we get the different Raman spectra that corresponds to Bruchite, anodized, and rutile with their characteristic Raman shifts. When we also calcinate the amorphous titania that are produced in the crystalline, we also get the characteristic diffraction data, or diffractogram, that characterizes each of the 3 forms. So that confirmed that we have phase pure titania in each of the 3 phases, depending on which of our aqueous media we employ to use the phase inversion temperature in the crystalline. We also did SEM, EDS to characterize the morphology. We have that of rutile and anodized as spherical particles, and basically the bruchite is a rod-like shape. And the EDS analysis allows you to understand that these are not only phase pure in terms of their structure, but also in terms of their chemistry. There's no impurities after we produce this titania, which is unique to the method. So in the next step in our experimental design, right, we have to use this titania to produce surface crystallized material, right? So to functionalize that material with the coordination complexes that are biphosphonate based. So we activated the material using UVVs. This happened, unfortunately, outside of the crystalline, so maybe that's something Technobis needs to think about. We used the PIT method to carry out the phase inversion temperature, and using that phase inversion temperature allows us to start the crystallization of that metal complex on top of the surface of the titanium. We did it for 5 minutes in one case, and in the other case we did it for, I think, 15 minutes. So we had different thicknesses of the shell that grew on top of the titanium core. That's our process. That's what we did. Raman spectroscopy and XRD again to allow you to see that we have chemical shifts, Raman shifts, and characteristic diffraction peaks for the salt calcium form 2 that crystallize on top of the rutile phase TiO2 in all of the 2 samples. Some pictures, some SEM pictures to show you how they look like. And here I have the control experiment, which is just a physical mixture of the coordination complex crystals and that of rutile titanium. The first TiO2 core salt shell, which only lasted for 15 minutes of 5 minutes of surface crystallization, and the TiO2 core nano salt shell that lasted 15 minutes. And as you can see, at 15 minutes we have overgrown of the crystals. So probably in terms of applications, we're gonna go with the 5 surface crystallization. Okay, so then I guess the last thing before I wrap up that I want to say is that we also did mapping, chemical mapping of the surface crystallization. And you can see here the control, where you can only see titanium and oxygen very discrete in that surface, in that phase. But in the other, the experimental chemical mapping, you have the titanium at the core, surrounded by calcium and phosphonate and oxygen that are part of the PB bio-CC. So we have, in fact, used surface crystallization to evenly distribute these bisphosphonate-based metal complex on the surface of the titanium core. So I guess with my story, what I wanted to tell you, right, what I wanted to convey is that we use this small-scale crystallization reactor, the crystalline as you might know it, coupled with the phase inversion temperature emulsification method to enable the development of several key materials. We have the salt-based, bisphosphonate-based metal complexes and the nano versions of these through phase inversion temperature. We have the phase pure titanium dioxide nanoparticles. These are the rutile, anodized, and brookite phase. This is the first method that can get you to all of these three phases with a starting point, and only differing on the calcination temperature. And then we also developed the titanium core that were surface crystallized with the coordination complex in a single particle. And I haven't shown you that data here, but we also probed their application against bone-related diseases, specifically metastatic breast cancer. And with that, I would like to thank, at that point, NSF and the Center for Interfacial Electrochemistry that allow us to carry out the titanium dioxide part of this experiment and provided funding, as well as the Crystallization Design Institute, which was the former lab I had with Torsten Stelzer. Thank you.